Now we want to move on to talking about some common functions, some common business models that will pop up throughout our applications this semester. We want to touch on price demand, revenue, cost, and profit functions, looking at how we can establish those different functions, and then use those to investigate our first application, which will be break-even analysis. So when we talk about price demand functions, those functions are going to be composed of two variables, x and p. In this case, a lowercase p, which will be an important distinction later on. X, and this will be true throughout our different applications, our different functions we'll introduce here. X will refer to items produced or sold. So we're producing some number of items, producing and selling some number of items, and we're going to be selling those items at some price point P. So P is going to refer to our price per item. When we talk about price demand functions, we're going to be looking at constructing some function P of X. So P will be our independent variable, and it will be a function of X as our independent variable. So in example 1, we're given that the price P in dollars and the demand X for a particular product are related by the equation given here. We want to express the price P in terms of the demand X. So essentially in this case, we're given a price demand function that's written in the form X of P. So in this case, X is our independent variable with P as our dependent variable. And what we want to do is update that function to be of the form P of X. Or essentially what that means is we want to solve for P. So starting with our given function, we can subtract 2,000 from both sides. Which will give us X minus 2,000 is equal to negative 10P. And then we can divide both sides by negative 10. To give us X over negative 10 minus 2,000 over negative 10 is equal to just P by itself. And then we can just reduce to say that P is equal to, or P of X is equal to X divided by negative 10 is going to give us negative 0.1X. And then negative 2,000 divided by negative 10 will give us positive 200. So we're just taking that given price demand function, and instead of having it be solved for X, rewriting it so that it's solved for P. So now we have a price demand function with X as our independent variable. We can also consider a case where, rather than just given a function and trying to solve, we can take some contextual information, or essentially a story problem, and then translate that information into our price demand function. So until recently, pretzels at a food truck cost $1.90 each. The food truck owner sold an average of 875 pretzels each Saturday. When the price was raised, their sales dropped. So we want to assume the relationship between price and demand is linear, and then generate a price demand function given this information. So a key piece of information here is that the relationship between those two variables can be assumed to be linear. So that means we're going to generate a linear equation, or an equation of the form y equals mx plus b. Or in this case, rather than y, we'll have p, that price, is equal to mx plus b. So then we need to take a look at the information that we're actually given in the problem. In this case, we have two different price points P, and then two different demand levels, or two different levels of product that we moved. So at our first price point, P, which was $1.90, they sold on average 875 pretzels. And then at the second price point, P sub 2, which was $2.35, that demand, or those sales, dropped to 750. So if we look at that setup, thinking about the fact that in place of y we're using p, what we have are essentially two coordinate pairs. x as our independent variable, p is our dependent variable. So we can fall back on the slope equation, which would be y2 minus y1 over x2 minus x1, or again in this case, y is being replaced by p. So what we'll have is the difference of our p values, those price points, divided by the difference of our sales level or demand levels, being sure to keep those pairings consistent. So if P2 comes first, then X2 needs to come first in that equation. So this would give us 0.45 over negative 125, or negative 0.0036. So that gives us the slope for our linear price demand equation. So we could go ahead and jot down the information that we know. We'll have an equation of the form P equals negative 0.0036x plus some intercept b, which means the next piece of information we need to solve for is that y-intercept b. In order to do that, we can plug in either of our given coordinate pairs. So in this case, I'm going to use p1 and x1. So I'll plug in p1 was 1.9, which is going to be equal to negative 0.0036 times the corresponding demand or sales level, in this case 875, plus b. So we know that either of these coordinate pairs should be a solution to this equation. So if we plug in that sales of 875 at a price point of $1.90, we can solve for what this missing value would be. So what we would do is go ahead and multiply these two numbers together and then add that value to the other side of the equation, which would end up giving us b is equal to 5.05, leaving us with a price demand equation of p of x is equal to negative 0.0036x plus 5.05.